Hello everyone. In the previous video, we have covered ramjet engine. But now there is a problem with the ramjet. Ramjet has zero static thrust. So we need to provide some thrust because static without a static thrust, how can the engine start on its own? So because of that, we designed turbojet engine, and that contains mainly first the inlet or the diffuser, then a compressor, and then a combustion chamber or burner, then a turbine, and after that, in some turbojets there will be afterburner, some it will not be. Next, nozzle. We define as states 1, 2, 3, 4, 5, 6, 7 like this, as shown here. Where 1 to 2 is through diffuser, 2 to 3 is the compressor, 3 to 4 is the burner, 4 to 5 is the turbine, 5 to 6 is the afterburner, 6 to 7 is the nozzle. And this is the HS diagram, or you can say the TS diagram, whatever you feel comfortable. I prefer to say HS diagram as something like this. Say from 1 to 2, from 1 to 3 to be specific, it is an isentropic process. 3 to 4 constant pressure process, 4 to 5 again an isentropic process, 5 to 6 constant pressure process, and 6 to 7 again an isentropic process. This is for an ideal turbojet. Again, same like a ramjet. We hate efficiencies, but yeah, we had to deal with it. There is a diffuser or inlet efficiency, which is given by this ideal, this say in general, efficiency is defined as the in, say if we are giving work to the system, it is input work by the actual work. Or if you are extracting work from the system, it is output work by the isentropic work. So for the diffuser, because we are giving some work, because the compression is happening, we have to give some work. We define it as ideal by real case, which is H naught 2 is by minus HA by H naught 2 minus HA. Similarly, for compressor, we give isentropic input work by actual input work. Turbine, actual output work by isentropic output work. And similarly for the nozzle. Now the burner also has an efficiency, same as the previous one, due to the incomplete combustion problems. After that, uh, again, you may have asked this question also, why we took stagnation pressure values but not, say, instead of 0.6, why not 6? Or even in the ramjet also you might have got this question. Because technically we had to involve the kinetic energies also. But stagnation values contain the kinetic energy term also within it. So that's why we take it. We take the stagnation quantity but not the static values. Now, again, we prefer large thrust and small thrust specific fuel consumption. So, now given flight speed, ambient conditions, PAT, and compression pressure ratio, P03 by P02, it is the design, it is a like parameter of a compressor, and then turbine inlet temperature, and this is fixed due to technological limitations like this T04 cannot be as high as you want, because if it is very high you need to employ the high metals, or sometimes we may not have a metal also to do that. So that's why uh, this is a fixed. So PA, TA, P0 3 by P0 2 and T4. Given this, our aim is to find F UE so that I can calculate this thrust and TSFC. So this video I'll pause it here. In the next video I'll be discussing about the engine analysis. Thank you.